Tal, and thanks to the organizers for the invitation. So this talk will be a continuation from Paul's talk yesterday, and talk about witness sets and pseudo-witness sets, and then end sort of with the project that the team is hopefully going to solve by the end of the week. There we go. So if you remember from Paul's talk, but if you don't, I'm telling you it again. Numerical algebraic geometry represents a variety by a witness set. So this is a geometric representation, and it's a triple. You need a polynomial system F. So I want to represent A. I need to know some defining equations for A, in particular that it's irreducible components of the variety defined by F. I'm going to intersect it with a linear space. This linear space should intersect transversely so that the number of intersection points is exactly the degree. During Claudio's talk, it was mentioned every algebraic geometry talk should have the twisted cubic. And so we're going to have the twisted cubic as the running example here. So how do I represent the twisted cubic in this numerical algebraic geometric framework? Is I need some defining equations. So let's say I take these two quadratics. Of course, everyone knows that's not the right ideal. I understand there's some extra components, but the beautiful thing about numerical algebraic geometry is it ignores that. So the twisted cubic is one of the irreducible components. I can intersect it. So it has dimension 1, so I can intersect it with a hyperplane. And of course, it'll intersect in 3 points. And we're going to represent these 3 points numerically on our computer. So I've truncated some floating point numbers here, so you can see that on the screen.
So do you generally take the number of polynomials to F cubic codimension?
That is to be numerically robust, then the number of polynomials is the codimension there.
Oh, you take it exactly?
Exactly the codimension. Because now things are robust. I can perturb things of the right codimension and it lives there.
So even if it's not a complete intersection?
If it's not a complete intersection, usually what you do is you randomize down to the right number of polynomials. And Bertini's theorem guarantees that this, and then you'll have some extra stuff. But the beautiful thing about this is witness sets localize the computations. So even though if you're randomized or if you didn't take the right polynomials and you have extra stuff, these things are effectively ignored. How do I get rid of this thing? There you go. This extra stuff is effectively ignored because I'm just looking at the intersection points that I have. Once we have this, now we want to be able to do computations from here. And so one computation we could take is, let's say I deform with a homotopy my linear space. As I deform my linear space, my points are going to change, and each one of these is going to give me new sample points on my variety. So what can I do with sample points? Well, you can do a lot of things with sample points, and I want to tell you 2 things that you can do with them. Of course, there are many more. You can try to compute vanishing polynomials, and you can try to study topological properties of your variety from sample points. So JM sort of alluded to this yesterday, maybe, in his talk about looking at 2x2 matrix multiplication. So you can think of 2x2 matrix multiplication living inside of C4 tensor C4 tensor C4. And now you want to look at what is the set of all border rank tensors inside of there. So that gives you this 6 secant variety inside here, and you can check that its dimension is 59. What are polynomials that vanish on this variety? I've given you a parameterization. Tell me polynomials that vanish. It's a very, very challenging computation. Macaulay 2 runs out of memory very quickly. Bertini doesn't compute vanishing polynomials, so you're kind of stuck here. But what I can do is I can cast this as an interpolation problem. Is I can generate sample points and try to compute polynomials that vanish on those sample points. Classical interpolation problem. Okay, so let's go back to our twisted cubic. Here are some points that lie on the twisted cubic. Suppose I'm looking for quadratics. Well, then you do the Veronese embedding. So take the point 1, 1, 1, 1, do the Veronese embedding, and you get all ones. 1 minus 1, 1 minus 1. Do the Veronese embedding, you get this vector. And now, quadratic polynomials that vanish correspond to null vectors in this matrix. And so hopefully you see the 3 null vectors corresponding to them. These 2 columns are equal, these 2 columns are equal, these 2 columns are equal, and so you get last. Okay, that's great. Works for the twisted cubic. Come back to this problem. Suppose I want to look for degree 18 polynomials. I need 400 quadrillion points in order to do this. Unfortunately, I can't generate 400 quadrillion points to be able to do this. So we need a new approach. And the idea is, instead of sampling points generally, let's use the sample points that lie on the same linear space. Let's restrict the linear space there. Okay, so change the problem. Instead of looking at polynomials that vanish on the entire variety, suppose I only look at polynomials that vanish on my witness set. If it was Cohen-Macaulay, then I would have an exact correspondence between these two. But in either case, you get upper bounds. Of course, if I have a polynomial that vanishes on A, it vanishes on these points. But if something vanishes on these points, it need not. But that's okay. Because now I've restricted to a 4-dimensional linear space, and the problem goes from 400 quadrillion to about 7,000. And that we can easily do. And so we generated sample points and then set up this matrix, and this matrix was full rank. So there are no polynomials of degree 18 or smaller that vanish on this variety. So that's a nice, simple technique to do that. If you go up to degree 19, then you can get 64 polynomials. I remember walking up to JM's office and telling him, there's 64 polynomials of degree 19. JM did his magic on representation theory and said exactly what they correspond to. So go search. JM searched and was able to find them. Good. And so we use this to prove that 2x2 matrix multiplication does not have border rank 6. It's already known to have rank and border rank 7 there. So witness sets allowed us to take this problem, which was impossible, turn it into something that we could get some information about, and then use representation theory or some other mathematical tool to be able to lift back to the original variety. I mentioned about Cohen-Macaulayness. You can turn this around. So if it's Cohen-Macaulay, then we know that there's a correspondence. You can turn this around to test for Cohen-Macaulayness. So what you do is you look at witness points, so intersect with a complementary codimension, and then remove one of those, so then it's a curve. And you can compare the Hilbert functions of the points with the curve up to the index of regularity of the points. So the points, is finite set. You can compute the index of regularity, and that gives you a way to test for arithmetically Cohen-Macaulayness, Gorenstein, and complete intersection. If you really want scheme structure, you can add Macaulay dual spaces onto this to be able to test for all of these things. And the beautiful part of this is only sample points. We only do this with sample points to do this computation. So from sample points, you can really get some really nice commutative algebra properties about the ideal. Okay, let's give another example of how we can use sample points. So one way we can use sample points is with this persistence homology. So we have our original points, and then you put balls on each one of those, and you grow the radii. And when they touch, then you connect them up. So here, all your points are distinct, and at some point they touch, and then at some point everyone is just collapsed down to a single thing. So if you have a provably dense sample, so if you know how dense your sample is, then you can actually prove theorems about the topological features that appear. And the beautiful thing is numerical algebraic geometry allows us to give these provably dense sampling here. So here's a picture of a quartic where this is provably dense up to some radius epsilon. Theoretically, the Betty numbers are 1, 0, 1. And what you can see in this persistence diagram, we have this section here colored. I don't really know what color it is showing up on the board here. On my computer, it's salmon colored, but I'm not sure what color that is. If you lie inside of that region, there's a proof that those features actually exist. So dimension 0 means it's connected. That one's well within the region. And then you have this other dot corresponding to the dimension 2, meaning that there's a void on the inside of this. That's right. So what you want from your sample point is, very good, thank you. So the question was, what does provably dense mean, and how do you prove that it's dense? Is that very good? So you give me an epsilon. 10 to the minus 3 is your epsilon. For every point in your variety, draw a ball of radius 10 to the minus 3 there, and I guarantee that there's a sample point inside of there. So, of course, there's lots of points on this. You can imagine what this surface looks like. There's lots of points that aren't shown here. But if you pick one of those points and draw a ball of radius 10 to the minus 3, one of my sample points will live inside of there. That's right. So you have to tell me the epsilon ahead of time, and then I will compute the sampling from you. And then you want to, let's say, halve the epsilon or divide by 10, then it'll add more points onto there. Yeah, very good question. This one here is not in the provable region. It doesn't actually exist, but you can kind of see that this looks like two dumbbells, and this one is sort of existing from the one side, and then eventually the two merge together. And so you get some indication for what the other features are that are happening, other than the ones that you can prove actually exist. That's right. So the general witness set is on a slice of it. And now in order to do this, we need real points. And so then what you're doing is you're computing critical points. And so that's all based on the curvature of your variety. So no. The algorithm that was used to generate this one is based on curvature. The general approach is some sort of optimization. And as you change your objective function, you get different distributions on your variety. Good question. Okay, what's another thing that we could do with our witness set is we could test whether a point lives inside of this variety or not. Of course, if I had defining equations, I would just plug it into my defining equations and see if it vanished. But the idea is we don't really have defining equations. So how do I test whether this given point is on the variety? Well, I just move my linear slice with a homotopy, move it in parallel until it passes through my point, and then I see, okay, this point moved by a homotopy here, this point moved by a homotopy there. They don't land on my point, so it's not in the variety. If it's in the variety, then I'll get points that go to it, and it turns out that the multiplicity is precisely the number of the paths that end there. So multiplicity 0 means I'm not in there. Multiplicity 1 is a smooth point, and so on. So you get some really nice tests from witness sets. But all of this required this initial F. I needed to know a polynomial system where this can live inside of it as some irreducible component. Please. So when you have some non-reduced components, suppose it's just a fat one. Yeah, that's right. It seems to me that if you start out with a couple of reduced points and then they convert to the same point, that I would actually see that point with multiplicity. Exactly. Just sit here, but I thought that sometimes these things disappeared somehow. No, as long as you have the right codimension. So if you're tracking points and you want to go to if you're tracking points and you want to go to a codimension, a fat point that's isolated, they have to go. They have to go there.
Paul was also, he was talking about just the vanilla version of it, where you don't have anything.
Yeah. 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 So as long as things behave on the right codimension, the multiplicity is precisely the number of paths. If you've done some randomization or other things, multiplicity goes up. That's right. That's right. Very good. Excellent. Okay. So all of this that I've talked about depended upon having a polynomial system F such that the variety that I want to study is some irreducible component inside of it. But as we've heard the past 2 days, there's a lot of varieties that we don't have defining equations for. You write down an image of a map. You have some rational parameterization. There's no defining equations naturally given to you. So how do I compute them? Well, one way is to try to use symbolic elimination. If it works, it's great. But this is a computationally intensive algorithm. So how can we perform computations without defining equations? Of course, we need some sort of description, and the description will be, it'll arise as some image. So for simplicity, let's assume that we just project onto the first k coordinates. In general, you can have any sort of matrix B, but let's assume we have the identity with the 0 there. So then my variety that I want to study, X, arises as the closure of the projection of A. So you can always sort of reduce down to this very simple case by adding more variables if you would like. Okay, so the closure here is taken in both the Euclidean and Zariski topologies. They behave the same way because this is the projection is a constructible set. So one of the simplest, easiest examples is just xy minus 1, and you project onto x. I can get every point in the image except when x is 0. And when I take the closure, then 0 comes in the closure. Either in the Euclidean or Zariski topology gives you the exact same thing. So what I want to do is I want to replace computations on the image with computations upstairs in the original variety that I started with. So this has led us to what are called pseudo-witness sets. Okay, so we're going to replace computations on the image with computations upstairs on the things that we have. Okay, so Berendt always says a variety walks in. What's the first question you ask? What is your dimension? Okay, so how do I compute the dimension? And how do so there's two varieties here. There's what's the dimension of the image, and then what is the dimension of the fiber. So GF is a general fiber. So whenever you see GF, that means general fiber. What's the dimension of the general fiber? It's really nice. The dimension of the image plus the dimension of the general fiber add up to the dimension that you started with. And if everything is nice, so if your original variety had multiplicity 1, then you can look at this by just null spaces. So pick a general point in A, in particular a witness point. The dimension of the null space is exactly the dimension of your variety. Your projection has this matrix B. You append that to the bottom, and now you get the dimension of the null space of that matrix. That tells you the dimension of the general fiber. And then, of course, you use this formula above and subtract the 2 to get the dimension of the image. So what this tells us is I now need to change my slice from being a general slice to one that respects these dimensions. So I need a slice that respects these dimensions there. Okay. So it's pseudo because I don't have a defining system. All I have is a system F for some variety A, and then this map pi, and I want to study the image of pi of A. I don't have defining equations for X. I only have defining equations for A. So now my linear space, instead of being a general linear space of that dimension, I add one extra condition that it has to respect the projection. So I know the dimension of X. I need to slice that many things downstairs. So a general one would map down generally. I want this to line up in the projection. So if I'd have taken this, this would have mapped down to a plane. That's not good because I want it to intersect my projection there in a curve. Okay? So you just change your linear space so that it respects the projection. And now what happens to the intersection points?
So what kind of calculation?
What kind of calculation is?
The restriction on the linear space.
It's a linear algebra computation. It's really easy, especially if you know linear map.
Oh, okay, then,
Yeah.
I was thinking of like,
No. Always, if it's a polynomial map, just add new variables, and then. Yeah, exactly. So every map that you see, every pi is linear, and I make it that way. Yeah, good. So everything is linear, and so I can line up in that linear space there. And now what happens when I compute this intersection? What happens when I intersect is I'm going to get points downstairs, and I'm going to get points upstairs. So the number of points upstairs is exactly the product of the degrees. So the degrees of the image times the degree of the general fiber. And then when you map them down, you get the degree many downstairs. So in this one, it's just a one-to-one map there, but the picture up above is a two-to-one map. So I'll get 2 points in W that map down to the same point below. What you're doing is, from a homotopy perspective, is taking your general slice and you're turning it so that it then maps down. When I take a general slice to something special, the number of roots can only go down, and the number that they go down I'll call n infinity. So it's the number of these homotopy paths that diverge to infinity when I go to this more special slice. I have no idea how to compute this other than to actually run the homotopy and compute it. Okay, let's give a very simple example. Suppose I want to take the parabola y minus x squared and project onto x. So y minus x squared has degree 2. So if I take a general slice, like this green one, I get 2 points. But now I want to turn it so that it aligns in my projection. And when I turn this general slice so that it becomes vertical, this intersection point just moves to there, where that intersection point moves to infinity. So I have 1 point at infinity. I had 2 points originally, and these both have degree 1. So just by thinking of a parabola, you can see as I turn this linear space so that it matches up with my projection, I get points off at infinity. You can do everything that you want with a witness set, with a pseudo witness set, hopefully. So you can construct membership tests. You can test for both membership in the closure as well as just in the image itself. So you get a little more refinement there, both in the image and in the closure. What happens if it's in the complement is things have to go off to infinity. So 0 is in the closure, means that I can get arbitrarily close to it, but if I try to get arbitrarily close to it, the points that go are off at infinity. So what you do is you homogenize. So you homogenize in the fiber variables, and so then in the fiber variables, this becomes a projective space, so it's nice and compact, and then you can test, is my homogenizing variable 0 or not 0? If the homogenizing variable is 0, that's a codimension 1 condition. And so then you can get these, you can actually compute these components of the closure of the complement of the image from its closure. So you can compute this. And in particular, in this case, you would just have this single point there. It arises from the closure that's not in the image. Okay, so now let's talk more about what the goal is for the rest of this week with the numerical algebraic geometry group, or at least part of it, is let's focus on just the hypersurface case. So in the hypersurface case, I have a single defining polynomial that's unique up to scale. What can I say about that polynomial given this pseudo witness set information? Okay, what we already know is its degree. Its degree is the number of these intersection points. So we already know its degree. Frank and I wrote down an algorithm. Numerically may not be the best, but theoretically it works. That allows you to compute its Newton polytope. So you can just find the Newton polytope without, from this information, without needing the actual defining polynomial. Taylor implemented this there. Exactly. And so what I'm interested in is looking at the complement of the hypersurface. So it's great to be able to be on the hypersurface, but usually I want to look at the complement. So why? Think about H being like a discriminant. Usually you don't want to lie on the discriminant. You want to lie on the complement of the discriminant. So how can I compute things in the complement without having H? Okay, so here's a application of this. Think about H as being like a discriminant, and so I want to compute real points in the complement of it. It doesn't have to be on Rn. You can do this on any algebraic set S. So like S could be the sphere or hypersphere or product of spheres or whatever you would like it to be, and you have some hypersurface there. And so the one way to do this is to compute these gradient flow roadmaps on them. So here my S is the Whitney umbrella. So I have some surface S, which is the Whitney umbrella, and the hypersurface that I want to remove is the handle. So I want to remove the handle from the Whitney umbrella and study the connected components that are left. If I had the defining equation for this H, call it little h, I would set up this routing function and compute its critical points. Since this thing is unbounded, I divide by a quadratic raised to a sufficiently high power. Here I've given some explicit description of the quadratic I'm interested in. Clearly, this thing never vanishes on the real numbers. 1 plus a distance is always greater than or equal to 1. So this compactifies everything. And so I get at least one critical point in every connected component. And in particular here, I get 3 critical points. You look at the eigenvalues and eigenvectors to see who's attracting and repelling. And so these are attracting, these are minima or maxima, depending on your view, whereas this one is a saddle. So following the gradient pass, I connect the 2 maxima through a saddle point due to the mountain pass there. This one is exactly it, because there are no higher order index saddles. It's the higher order index saddles that are the problem. So if you have things of index 2 or 3, now how do you get from index 3 to index 2 to index 1 to index 0? That's numerically unstable. The beautiful thing is index 1, there's only one direction to go in, and it's a numerically stable operation. Higher order. So this one is exactly what you want. Okay, so we've talked about witness sets. So witness sets give us this information over the complex numbers. We can mirror this with these kinds of gradient roadmaps. So instead of an irreducible variety, we're looking at a smoothly connected component. Instead of a linear space, we're looking at this function. Instead of the intersection points, we're looking at critical points. Over here, the degree was the number of witness points. And as Paul mentioned yesterday, we can get the Euler characteristic from our critical points. So there's some sort of invariant that shows up in this information. I described how we can use this linear space to move around to test membership. And you can do the same thing or a mirror here. Suppose this is your point. You do a gradient flow. It has to end at a critical point. And therefore, once you know which critical point it is, you know which connected component you live in. So at least of these objects on the witness set that I told you, this thing mirrors everything that we want there. Okay. It was during Frank's conference last year here. We were over at Prenup Pub, and Barrett asked the question, how many connected components are there in the complement of the Klepsch cubic with the 27 lines removed? Of course, he knew the answer. He was just testing. Barrett always knows the answer there, and wrote down, had it in a paper there. I first did this computation in R3, and then Barrett quickly said, you should do it in projective space instead of affine space. And so once you do it in the right space, you have the Klepsch cubic. Here's an affine, the affine form that I used. You remove the 27 lines, and you get 120 critical points. Since this is actually a hyperplane arrangement on the Klepsch cubic, everything is a maxima. And so you only have 1 point for each connected component. So it works out beautifully. So every connected component has exactly one connected component, exactly one critical point. So if I was going to do a gradient flow from any point, it would always end at that single mountaintop. So that's really nice. What was the hardest part of this computation? The hardest part of this computation was computing the polynomial that defined the 27 lines on the Klepsch cubic. It wasn't computing the critical points. It was computing the polynomial that I wanted to remove. So that's the hard part here, is computing these polynomials. Let me give you another example. It showed up on the archive within the past month. Okay, so I'm on sabbatical this year. And of course, I go visit Elizabeth in Hawaii. And what better thing to do in Hawaii than study the coral reefs in Hawaii? And so we studied the coral reefs both by swimming as well as mathematically. And so here's a dynamical system to describe the coral reef when you have two kinds of bacteria. One that tries to kill it, which is a pathogenic, and one that lives sort of mutually beneficial to both. And so that'll be Z, the mutualistic bacteria. Everyone is happy when Z is there. The coral is not happy when Y is there. And so then we can compute the hypersurface boundary corresponding to the Routh-Hurwitz conditions, and then look at the complement. So in this case, the boundary has degree 145. Macaulay 2 was able to compute this with some tricks that we did, and it factored into actually 31 factors. What's interesting is in this picture I'm showing, there's a small region in here where we can actually prove that there's only limit cycles. So we used algebra to be able to give some analysis of this where we can prove there are only limit cycles in this small region. So again, the hardest part of this computation was computing this boundary polynomial. Okay, so the challenge usually is computing this boundary polynomial. So can we redo these computations with a witness set to be able to avoid having to compute this polynomial? Of course, it's going to be challenging, but there are many smart people in our group. And so hopefully by the end of this week, we can perform computations on the complement of the hypersurface just using this pseudo-witness set. Okay, so of course, the quadratic discriminant arises from elimination, but I don't want the polynomial b squared minus 4ac. I want to study the complement of it. Because this has two connected components, one where there's 2 real and one where there's 0 real. That's really what I want to study. How many real solutions are there? And so I want to be able to study the complement of this hypersurface. So let me end there. Thank you.